So this is the supplementary project we did for Project 3. We decided to import our own data set and see how we can use the vectorizers and perform a classification problem. Um, so the data set that we grabbed was a custom-made data set that someone posted onto Kaggle that was about 60,000 tweets by members of Congress. So almost every member of Congress, 433 members of Congress, the 200 most recent tweets they had made in May of 2018 is what makes up the data set. So the idea here is, can we look at these congressmen's tweet and somehow predict that what their party representation is? So some of the tweets in the data set are retweets that the congressmen are tweeting out. So that may affect our data a little, but we're going to assume that the ideology of a tweet that is being retweeted by the congressman probably closely aligns with their ideology. Um, so let's get into it. So to start, we decide to grab all the Twitter features. When we run our vectorizer, we don't want to be plugging our Twitter features into things like a bigram creation. So we have to extract all of our hashtags, all of our handles, and we have to extract all of the HTML, the HTTP tags that people have posted. Um, we do a lot of exploratory data analysis. You'll see that we look at bigrams that we expect to have an effect, and we show you how many Republicans tweet it versus Democrats tweet it. Due to the size of the data, we had to make a choice. If we had run the vectorizer on this entire data set, we did not have the computational resources. So it was either take a smaller subsample, or the route that we went was that we decided to create a custom vocabulary to insert into our vectorizer. So that custom vocabulary, as you'll see, pretty much consisted of the top n-grams that we saw that were tweeted throughout the data set. So here we have our functions pretty much so that we can take our initial data set, which was just the congressman's name, his party, and the tweet, and turn it into a format where we can use it. So we grab all the Twitter handles, all the Twitter tags, and all the Twitter handles, and we extract them into their own columns. If something was retweeted, we keep track of how many times it was retweeted. We do all this stuff, and then we clean out all those things from a column so that we could eventually use that column to run the vectorizer on. And then we have a make bigrams here, which kind of just makes us custom bigrams so we can look through our bigrams. So here's what the data set looks like after we call our function. And it pretty much gives us back the tweet, how many times it was retweeted, the handles, the hashtags, the links, and then we created these custom features of total characters and average word length. You'll see below we break these down a little bit. You can see that the average word length is about the same for both parties, whereas the total character seems to be a little bit bigger for Democrats. So the total characters actually is the characters used when we take out all of the Twitter handles. And the average word length, the idea behind it is perhaps certain people are using bigger words. When they're tweeting. I don't know if that would necessarily be an ideological thing, but we figured let's take a look at it. So here we can see the breakdown by Democrats and Republicans for average word size. It looks like there's some difference between the histograms, but they're pretty similar. And I think the same thing can be said of the average characters used. But if anything, we are seeing that there is a little bit of a difference here in the peak of average character use, and the Democrats use or more often to use 140-ish characters. So, just to give it an idea of like what the idea is behind grabbing these bigrams, we do a search for all forms of the word pro-life, and then we print out how many times that word was used by a Republican versus a Democrat. And you can see that out of 37 times the word pro-life was used, 32 times was used by a Republican, and 5 times it was used by a Democrat, which we would expect. So from here, we tokenize and we create our bigrams. So we add in here the tokenized, the bigrams, and the engrams. So the bigrams is just simply all the bigrams. The tokenized is the single words, and the engrams is a combination of both. Now, the reason we need to do this outside the vectorizer again is that we want to create a custom dictionary. There's probably something that we should address before we go any further, in that this custom dictionary is being built on the entire data set, which may bias our results. But we kind of just used the Twitter features that were reused frequently. So I don't know how much it would have made a difference if we had split off our training and test set, and I don't know if it matters if we create a lexicon of words that are apt to identifying our end goal. It shouldn't necessarily matter. We could have a 1 million Twitter handles or Twitter features if they are valuable to us. Um, but so here we're looking at the single words, and what we decided was, okay, if a single word is used over 50 times, excluding stop words and things like that, that we'll keep it. So out of a total of 30,000 words, we're keeping 2,100 features that were used over 50 times, and then we look at the bigrams. Out of a total of I think it's down here. Out of a total of 410,000 total combinations of bigrams, we decide to keep 2,024. These are the bigrams that were used over 20 times. Now here we just kind of displayed that at first, the way that we created the bigrams, it wasn't actually working. So what we had to do was we had to then do a regex to say, find me a space between words. If you don't find a space between words, discard it. And that gave us our clean bigram data set down here. So now we have to combine these two, and that's what's here. So this is going to be our vocabulary that we're going to insert into the vectorizer. We did not stem the words. I don't know if it would have made that large of a difference to have stemmed the words, but the difficulty in stemming the words was that the vectorizer doesn't behave well when we're using data frames. So you have to customize the function. And we couldn't figure out how to customize the function and add in the stemming. But either way, it shouldn't make that much of a difference. So here we're just going to look at things, and we can see, what hashtags are used most frequently, and how do they break down. And we can see that, when we see the word hashtag net neutrality, 263 times out of 267 times, it's a Democrat. You can kind of see that it's actually printed several times here. That's because this function is just looking through every single row and saying, if you find the word we're looking for, then show it to me with its aggregated statistics. So whoever this tweet was made by, he used the word neutrality, as did this person. Looking at the links didn't actually show anything. I think the most used link was used about 18 times, so we just discarded the links. I mean, maybe it's cool to look at and see what people are posting for that, but I mean, 60,000 tweets, no one retweeted something more than 20. No one posted a link more than 20 times. Looking at the so at the tags. So you can see that here, once again, we're seeing that hopefully our model is going to recognize these things. That Represent Darren Soda, for instance, was 92 times as a Democrat and 2 times as used as a Republican. Now, this may be another example of where our classification model is being biased, because that is his name. And quite obviously, most of the time that it's being used by that person, and the model's probably going to be really good at capturing that. But once again, it might not matter. But maybe it does. So if our data set included, tweets from random people, then, both Democratic and Republican constituents would likely have used his Twitter handle. So this definitely wouldn't be able to extrapolate out to a data set like that. So from here, what we had to do was we had to turn our Twitter columns into individualized hot encoded features. So all it's done here is this is just a data sanity check to make sure that as we made this transfer over, that everything worked out. So we're saying, looking at the original data frame, make sure that these are all tax reform in the new data frame. And as you can see, when we look at it, it fits. And same thing here for the ads. So now this is our new data set. So our new data set includes 1,000 columns of mostly Twitter handles and Twitter Twitter hashtags, and then our custom encoded features and everything we had before. From here, we decide to take a look at which Twitter features um, seem to be the most representative of a Republican or a Democratic. And the way we did this was we said, okay, if the Twitter feature had been used over 200 times, and if the gap between how it was used by a Democrat or a Republican was over 50%. So, in other words, um, if it was used 10 times and 8 times it was used to identify one party, 2 times to identify another party, it would make it into our filter. So these are like the top features that we would expect our model to be able to capture. So overall, I think there's 23 or so features listed here. And the reason we show this here is after we run our models and we run our tree models, we want to extract those variable importance features and see how many of these ended up in what our model decides are important. Because in the end, there's going to be something around probably 4,000 features, I think, or 5,000 features. So if these features, which we see here, end up in the variable importance in our models, it's probably a good sign that our model is picking up on these things. From here, we just decided to do some word clouds. And I think they're pretty self-explanatory, but they do show obviously, like hashtags like Obamacare are being hashtagged by the Republican Party. Tax reforms being by the Republican Party. Things like net neutrality, as we saw before, are a big term for the Democratic Party. In terms of ads, same thing. We can see the Republican Party. We can see the Democratic Party. And then here we are, and we're ready to build our classifier. So what we do is we train several models, and we do it with some of them with a count vectorizer, and then some of them with a TF-IDF. The models we train we just do run a simple naive Bayes, then we run logistic regression with a little bit of tune-in for regularization, and then we run a random forest and a gradient boosted. As you can see from the results, and this is in the count vectorizer, the naive Bayes performs at about 74% accuracy, and logistic regression performs a little better, and our random forest performs pretty poorly. From what I understand, random forest isn't that great at performing on sparse data, so perhaps that has to do with it. We didn't necessarily tune it that well, but overall the results are sort of disappointing. I don't know how disappointing the results are in terms of the 75% accuracy. I guess that's about a 50% lift on what we would on simple guessing. Um, but at the same time, there may be some bias in our model considering we trained our vocabulary on the entire data set. The gradient boosted machine also performs pretty poorly, and to be honest, it took a really long time. The gradient boosted machine was supposed to perform better on this from our research, but it did not. Here, what we did was we grabbed the top 50 features of both the gradient boosted machine and our random forest. And we combined the two to say, of these two top 50s, what features are you two saying are in the top 50? So this is the shared list of features. And what we're going to do is we're going to compare this list to the list of 23 features that we looked at earlier. But before we do that, here all we did was we tuned the random forest, and you can see the performance wasn't that much better. I mean, where it performed better was when the depth went to none, but that's probably at overfitting, and that's definitely the bias of having the vocabulary. So I don't think we could really consider that, as our results. And we used the TF-IDF, and it performs slightly better. overall than the count vectorizer, but performance wasn't that much better. I think that makes sense because most of our features were, the top features, so they already were very similar in terms of their TF-IDF values, I think. Um, from here, we're just displaying that's for the TF-IDF, the random forests, and here this is our comparison. So this is essentially out of 22 possible features which we thought in exploratory data analysis were very important. Actually, 16 of them showed up in this combined top 50 list that we just created. So what that tells us is that our model, even though it's not that accurate, it is performing in a way that we would expect it to perform. And perhaps what it just needs is it needs more data. So we couldn't build out a feature list that does tens of thousands of columns. Um, but just from these 4,000, it is recognizing them, right? So if there is some way where we can get more computational resources, perhaps those Twitter symbols and everything could help us get more accuracy. So as you can see here, the classification report, the logistic regression seems to blow the random forest out of the water. But yeah, that's our project, and thank you, and I hope you enjoyed it.